Hi, in this video I'm going to do a Monte Carlo simulation of a valuation model. In fact, you can apply what I'm discussing here to any model you have as long as the model has some inputs and outputs, of course. Here I'm applying it to a DCF valuation model since I believe it's an important and extremely useful application of a Monte Carlo simulation, something that's surprisingly rarely done in practice. So let me first highlight how we typically account or deal with uncertainty in our models. Here, for example, I have a DCF valuation model. This one, like any other DCF model, has some inputs and assumptions. As you can see, the inputs or assumptions in this specific model are the annual growth rate of the whole addressable market in the next 10 years, the risk-free rate, return on capital in the terminal year, the probability of failure, the market share of the company in the terminal year, and so on. Now, of course, we have to assign some numbers to these inputs to be able to get an output, which is, in this case, our output is our estimated value per share for the business. We want to know how much each share of the company worth. The way we typically, or better to say almost always do this, is to assign our best guesses for each input and get an estimated price for our base case scenario. For instance, here, assume that my best guess is 10% market growth rate and 30% as the market share for the economy, for the company in 10 years. Similar for other assumptions as you see here. So I use these as inputs and get an estimated price per share using these assumptions. However, I'm really not sure about these numbers. So what if the growth rate turns out to be 8% instead of 10%? What if the market share would be 40% instead of 30%? The way we deal with these types of uncertainty is to have a sensitivity analysis table, which looks like this. We pick two of our assumptions for which we are most uncertain about, and then discretely assign them as some other numbers, and we see what our estimated price is given these new assumptions. We finally try to pick a somewhat arbitrary range among these outcomes as the fair price range, for example. There are several big issues with this approach. The first one is that in Excel, you cannot do such an analysis using more than 2 inputs. If I were uncertain about 4 of these inputs, there is no way to do this kind of sensitivity analysis table in Excel. Second, and more importantly, these sensitivity analyses are very uninformative, honestly. Imagine for the market growth, we are, say, 60% sure that it's 10%, but we believe there is a 20% chance that it's 5% and 20% chance that it's 15%. So here we are more sure that the middle one has the highest likelihood of realizing. On the other hand, for the market share, assume that we really have no strong idea, assume that it is equally likely that the company has 20%, 30%, or 40% of the market share. You see now why we get into trouble. How can we interpret these output numbers? And these are very simple examples, and in reality, there may be many other types of probability distributions we have to face with. In addition, for risk management purposes, we want to know what is the likelihood that the price falls below a certain amount, say $30 per share. Or what is the likelihood that the value of the business is more than a threshold, for example, $100 per share. The regular sensitivity or scenario analysis are, say, cute and easy to do, but unfortunately provide us with very little insights regarding these very important questions. This is where Monte Carlo simulation comes to help us. The intuition behind the Monte Carlo simulation is super simple. We assign a probability distribution function to each input depending on their nature and our opinion about the potential realizations. Probability distribution functions are essentially a set of possible outcomes together with their probability of occurring. The two examples I made about the growth rates and the market shares are two examples of probability distributions. So all we need to do is to decide what are our input variables and what their probability distribution looks like. Then we pick a random variable out of that distribution and use it in the model as an input and get the outcome of the model. We repeat this for, say, 1000 times, and hence we get 1000 estimated price per share. This, in fact, gives us a distribution for our outcome variable instead of one or a few numbers. So we can compute what is the minimum, maximum, or median value given the uncertainty we are facing in our important assumptions. Or we can compute what is the likelihood that the price falls below or exceed thresholds, for example. So this is a general introduction, and if you are new to this, it's totally normal to feel a bit lost. I am sure as we go through the project step by step, you will feel more and more comfortable since all becomes concrete when we work with the data. Now let's go to Jupyter Notebook to start coding. We first need to import the necessary packages. This includes, of course, pandas, random, and numpy, and so on, as you see here, but importantly, Excel wings, since it's going to be extremely useful here for us. If you're not familiar with the basics of Excel wings, I have provided in the description a link to a video showing the basics of Excel wings. After importing this, we first connect to our workbook, which in this case is our valuation model. As discussed also in the previous introduction to Excel wings video, we use the book object to connect to the workbook. If the Excel file is in the same folder as our codes, we do not need to provide the full path of the file. So in here, my Excel file is called DCF_model, but note that if I only pass the name, I will get an error. I would need to pass the file name as well as the extension for the file to work. So I add the extension here as well, and now it is fine. I can also take a look at the sheets inside my workbook, and indeed there is one sheet and it is called sheet 1. So now let's assign a name to this sheet. Let's call it DCF_sheet. Before we start our simulation, let's do a simple exercise so we understand what is really going to happen when we do our simulation. Let's assume that I have one input, and that's the growth rate. Now let's obtain the value for a growth rate that is now in the cell E2 and call it G_rate, standing for a growth rate. Let's report it to make sure that it's indeed the correct number. Yes, it's 10.39%. Now that we have our input variable, let's get our output, which is the value per share and is in B45, and let's call it price. If you remember from the previous video, when we have accounting or currency formats, Excel wings brings the number with decimal format. We need to take the float of that to obtain the correct number. Now that we have both the inputs and output, I can easily assign a new value to the input and see what happens to the output. For example, instead of 10% growth rate, let's assign 8% and then repeat what we did before to get the estimated price per share using 8% growth rate instead of 10%. If we copy all we had above, we get the new price, which is $44.88. So what we will be doing in the simulation is doing such an exercise for many repetitions. The only difference is that our inputs will be selected randomly based on a specific simulation we choose for the inputs. In this video, we will be using only one variable input, which is the growth rate, and we will use the normal distribution for it. In the next videos, we will see how such a process could be easily extended to include as many inputs as we want, and also we will discuss how to choose appropriate distributions for different input variables. For now, let's try to get the main insights right. Afterwards, the life will be easy. So, and now let's add a new sheet and name it simulation, where we will copy our simulation results. How do we add a sheet? We used .add attribute and pass the name of the new sheet. And let's call it sim underline sheet, standing for simulation sheet. If I run this, a new sheet will be created named simulation. Now, as I said, we will pretend that we have only one uncertain input, and it's the growth rate. I'm going to assume that the growth rate on average is 10%, but it follows a normal distribution with a standard deviation of 3%. This effectively means that 95% of times the growth rate would be in the range of 4% and 16%. So it's a wide range because I am really uncertain about this, but on average it is 10%. Note that since it's a normal distribution, a higher likelihood will be attached to the numbers in the middle of the range rather than the ones on the side. So I can draw a random number from such a distribution by using the random normal variate and pass the mean and standard deviation to it. Let's show the growth rate and run this cell for several times to see how the generated random variables based on this distribution look like. So now all we need to do is to draw many of these numbers from this distribution and do what we did in the previous example, which means to use these random draws as the growth rate in the model and obtain the estimated price using that growth rate. So the first thing we need to decide is how many times we would like to repeat this process. The higher the number, the more sensible the results would be. The number should be at least, say, about 1,000, but it's best to be 5,000 or 10,000 or even more. Of course, as the number of simulations go up, the time to run the simulation will be longer and longer. So let's start with 100 repetitions, but I warn you that the results will look strange with such a low number. Afterwards, when we see that the code is working, we will increase the number of our simulations. Now I need to have a loop to repeat the process as many times as the number of simulations. Each time I generate a new growth rate based on the normal distribution I have decided, then I replace the value of growth rate in the model, which is in E2, with this randomly generated number. When I do that, my Excel model will automatically be updated with this new input, and therefore I can collect the estimated price in B45 as the output. Now I want all the estimated prices to be kept in a list to have them all together. I can start with an empty list called DCF underline values, and then at the end of each round of repetition I append the prices to that list. I can also keep all the randomly generated growth rate in another list just to have them at hand in case it's needed. I would like to copy the list of all growth rates and associated price estimate in this simulation sheet. But first, let's see how the list of DCF values look like. So these are the 100 estimated prices that we collected in the list called DCF values. Now let's try to copy this list to our Excel sheet starting from cell A1 just to see how it looks like. Well, I need to specify a value here. When I run the code, as you see, the list is copied, but in the first row. We usually in Excel would like to have these things in a column. Now I can transpose this list so that it will be copied in a column in Excel. Let's do the same for growth rates as well. Now let's copy the DCF values in cell C2. It's in C2 since I want to add the column titles afterwards. And let's add the growth rates in A2. So now I would like to clear the simulation sheet before running the simulation again so that I don't mix up the old and new numbers together. To do that, we use the clear attribute before running our simulation. Now everything looks fine, I think. Let's run the simulation and then copy the values we obtain into the Excel sheet. Okay, all is fine. Now I can assign titles to each column so I know what each column is reporting. The first one is growth rate and the second one is estimated value per share. Now that we have the simulated result, let's use data frames to both get a sense of how data frames could be used and also create some graphs and descriptive statistics, some useful ones. We define our data frame called DF, which is in fact the DCF underlying values we have obtained from simulation. Let's see some first records of this data frame. Let's assign a meaningful name to the column and call it simulated prices. Now let's try to have a plot of how the distribution of the estimated prices look like. We can use histogram plots. Instead of counting the numbers on the y-axis, we can report density by assigning a true to density option. We can also assign a specific number to bins rather than allowing the program to choose the bins. As I said, the results look weird now since the number of simulations is very little, but we will run this soon with a meaningful number of repetitions and it will be fine. Now, let's also define a label for our axis and assign an appropriate name for the plot. I can also add a vertical line showing us the mean of the estimated prices. As you can see, it looks that the mean is a bit higher than 50, maybe it's 51 or $52 per share. Now we can copy this plot to our Excel sheet. We can decide where exactly we want it to go. Let's send it so that its top left corner is in the cell H2. As we discussed in the introduction to Excel Wings video, we can use the pictures.add to add such a figure to our Excel sheet. So let's run this. Here we go. We have the distribution of our estimated prices. It would be very useful to also have detailed descriptive statistics here. We can use the function describe that returns the descriptive statistics of our data. Let's call this a desc underline stat, standing for descriptive statistics, and then copy them in a range E2. Here I can see the mean, standard deviation, and the different percentiles of the distribution, for example. Now let's try using NumPy to create a cumulative distribution function. This will help us answer questions like what is the likelihood that the price falls below a certain threshold, for example. We first need to sort our estimated prices. Our x values are simply the sorted data, which is the estimated prices, and the y values correspond to the proportion of data points less than each data point. And we plot the x and y, and let's show it. Welcome error. Well, it seems a parenthesis is missing. As you see, the y-axis ranges from 0 to 1, representing the probability. In fact, now this looks like a line plot because by default the dots are connected, but let's make each data point a separate dot to see the correct view. So here our x-axis represents the value per share and the y-axis represents the probability of having less than or equal to each specific price. For example, according to this graph, the probability of the price falling below $40 is around 20% or perhaps 18% or so. Now let's copy this plot also in Excel. Again, we can decide where we copy it. Let's copy it in H21, just below the other graph. We can, of course, easily copy the code we wrote for the other plot and adjust it slightly for this plot. Okay, all is fine, I think. Let's run it. Here we go. Now that our code seems to work well, let's go back and increase the number of simulations so that we get more meaningful outcomes. We can increase the number to 5,000, for example. Let's run the simulation. You can see that the simulation is working by looking at the Excel model. Our input value for the growth rate is changing for each random draw. And of course, it feeds through the model and gives a new estimate of value per share in each round. This will take some time to finish. And when it finishes all the 5,000 simulations, we can see the outputs again in our Excel sheet. Now the plots indeed look much nicer since we have many more data points. We can easily see what is the likelihood that the price ends up being below a threshold. We can see the maximum value we could get and the whole distribution of possible value per shares. So remember, we did this simulation for only one uncertain input and one specific probability distribution, which was a normal distribution. In the next videos, we will try to clean up the code we wrote here, fix some issues that are in the codes, and we will make a nice function that does all these for us. We will also extend this logic to several uncertain input variables and discuss how to choose an appropriate distribution for each input. I hope this video was useful and take care.